Welcome to Chapter 15 on binary addition. A binary adder is a combinational circuit. It has a parameter n that specifies the length of the input. The input consists of two binary strings, A and B, each of length n, and a single bit C0. The output is a binary string S, also of n bits, and a bit Cn. The functionality of the binary adder is that you have the following relation between the inputs and the outputs. The number represented by A in binary representation plus the number represented by B in binary representation plus C0 must equal the number represented by S in binary representation plus Cn times 2 to the n. It is very common to use the following terminology when we talk about addition, about binary addition. We refer to A and B, to the two input strings A and B, as addends. We refer to the bit C0 as the carry in bit. We refer to the bit Cn as the carry out bit. And we refer to the string S as the sum string, or the sum. One question that you may ask is whether it is true that for every A, B, and C0, there exists an S and Cn such that this equality holds. If this does not hold, then we would have a situation in which we have defined a circuit that is not well defined. And we want to show that indeed, for every A, B, and C0, there exists an S and Cn such that the required equality holds. Otherwise, adder n would not be well defined. The proof is very simple. Notice that the number represented by A is between 0 and 2 to the n minus 1. This follows from binary representation. Same holds for B, and C0 is between 0 and 1. So, when we add things together, we know that the sum of A plus B plus C0 is between 0 and 2 times 2 to the power of n minus 1 plus 1, which amounts to 2 to the power of n plus 1 minus 1. Now let's look at the other side, where we have S and Cn. S and Cn together can represent all numbers in the range 0, 1, 2, 2 to the n plus 1 minus 1. This again follows from binary representation. Therefore, the adder is well defined, because whatever this amounts to, we can represent it with S and Cn. Now, how do we design adders? Let's start with the simplest case in which n equals 1. Adder 1 is often called a full adder. A full adder is a combinational circuit with three inputs, x, y, z, each of which is a single bit, two outputs, C and S, each of which is a single bit, and we have the following connection between the inputs and the outputs. The sum of the inputs should equal S plus 2 times C. Now, you could implement a full adder any way you wish, but here's a suggestion on how to implement a full adder. The S, the sum bit, is simply the XOR of the inputs. C, the carry out bit, is the AND of the three products, XY, YZ, XZ. We often refer to S as the sum output and to C as the carry out output of a full adder. Now we want to design an adder for n bits. We will start with a very simple design called the Ripplecarry adder, in short RCA in parentheses n, where n refers to the length of the input. The design of an RCA-N is very simple. You cascade n full adders. The full adder with index 0 is fed by C0, A0, and B0. It outputs S0, and its carry bit is denoted by C1. We feed A1, B1, and C1 to full adder 1. Its sum bit is denoted by S1. Its carry bit is denoted by C2, and so on and so forth, until we have reached full adder n minus 1, its sum output is denoted by Sn minus 1, and its carry output is denoted by Cn. Now, if you think about it for a second, this design implements the way that we perform addition by hand. We scan the bits from the least significant bits to the most significant bits, add them one by one, may have a carry, add them, may have a carry, add them, may have a carry, and so on. So in fact, this design is the same addition algorithm that we learned in elementary school. Now, the notation that we use here, we write C1, C2, and so on. The indices that we attach to the various bits always equal their weight. By weight, I mean the following. I look at the number represented, say, by A in binary representation. It is this power series. And I say that the weight of AI is 2 to the power of I because this is the number by which I multiply AI in this power series. So this is the weight of AI. Do not confuse the weight of a signal or a weight of a bit with the Hamming weight. It has nothing to do with it. The weight here is simply powers of 2 that appear in the number that is attached to a binary string in binary representation. So if I look at it at C2, its weight is 2 to the power of 2, namely 4. Okay, we want to prove that the RCA is correct, namely that it performs addition. Namely, we want to prove that S plus 2 to the power of n times Cn equals A plus B plus C0. We prove this by induction on n. The induction basis for n equals 1, well, our RCA is simply a full adder, and we already showed that a full adder performs addition of 1 bit. Let's skip to the, let's describe the reduction step. So this is a recursive definition. So I started outlining the proof before I describe the circuit. So let's describe the circuit first. RCA for the base case, 1 is simply a full adder. And the reduction step is as follows. I take the Ripplecarry adder for n minus 1 bits. I feed it with C0 and the first n minus 1 bits of A and B. I take the output of the Ripplecarry adder, I denote it by Cn minus 1. I feed it into my full adder, the last full adder, together with An minus 1, Bn minus 1, and I get these two outputs. So notice that when I open this recursion, I will get the same Ripplecarry adder that I have here in the depiction. So this part, just to make things clear, this part is in fact an RCA of n minus 1 bits, okay? And I cascade to it another full adder. So this is exactly the same reduction step that you see over here. Okay, so I hope you see that this design and this design are the same one. And now we want to prove that it is correct. Okay, so we want to prove that the RCA n is a correct implementation of adder n, and we will use this recursive definition rather than the definition in which we had these ... dots in the middle. Okay? Good. How do we prove the correctness of the RCA n? Surprisingly, it's not such a short proof. Okay? On the other hand, you should be very satisfied because the same proof proves the correctness of the standard addition algorithm that you use. And I guess this would be the first time that you see such a proof. Okay, so let's prove the correctness of the RCA. It will be by induction on n. The induction basis for n equals 1. Well, a full adder is correct. You can check that manually. The induction hypothesis states that RCA n-1 is correct. And now we want to prove the induction step. Okay, so recall, the thing we want to prove is this equality. So let's start with the right-hand side. A plus B plus C0. Let's decompose A into two parts, the most significant bit and the remaining bits. The weight of the most significant bit is 2 to the power of n-1, and here we have the number which is represented by the bits of A from 0 to n-2. We do the same partitioning to B. So here's the most significant bit of B, and here are the remaining bits of B, and we copied C, C0. Now we can apply the induction hypothesis. The induction hypothesis is applied to the n-1 bits of A, the n-1 bits of B, and C0. And the induction hypothesis tells us that this RCA is correct, the RCA for n-1. This is the induction hypothesis. So we know that this fellow marked in yellow equals this fellow marked in yellow. This would be the first n-1 bits of S and the carry bit n-1, which is sent to the full adder, to the last full adder. So let's see where this Cn-1 resides. This is your Cn-1. We fed the first n-1 bits of A and B into the RCA n-1 together with C0. We got the first n-1 bits of S and the carry bit Cn-1, whose weight is 2 to the power of n-1. This fellow is sent to this full adder. Okay, so we have equality between these two yellow parts. This is the induction hypothesis when applied to RCA n-1. Okay, let's remove the marking of the yellow things. We're now in this line. What we do in this line is we simply take the Cn-1 and we put it here in the parentheses. It is multiplied by 2 to the power of n-1. All the rest we simply copied. Okay, this part we copy. And now we look at these three bits. What do we know about these three bits? An-1, Bn-1, and Cn-1. Well, these are the bits which are fed to the last full adder. And the last full adder, we know what its functionality is. So we can replace these three bits by Sn-1 plus 2 times Cn, because this is the functionality of the full adder, the last full adder. Okay. Now, Sn-1 is multiplied by 2 to the power of n-1. This is its weight. So we can, instead of writing it like this, we can put Sn-1 as the most significant bit of S. Okay, so we take the n-1 bits from here, the last bit from here, and we just write it together, combined in this fashion. Now 2 to the power of n-1 times 2 is 2 to the power of n, multiplied by Cn, and this is exactly the left-hand side that we need to prove equality to this part. And that completes the proof. Let's do a delay and cost analysis of an RCA-N. Well, the RCA simply consists of n full adders. Each full adder has a constant cost, so the cost of the RCA-N is linear. What about the delay? Well, the longest path in an RCA-N consists of n full adders. This is the path that traverses all of the full adders. Here you can see it. Sorry. You can see the path. Let's mark it. It would go like this through all the full adders. Okay, so this is a path that traverses all of the full adders, and therefore the delay is n times the delay of a full adder. Okay? Okay, so having linear cost is pretty good, as you will see later. What about the delay? Does this make sense? Well, if you look at modern microprocessors, the clock rates in these modern microprocessors correspond to a delay of, say, 15 to 20 gates. And microprocessors can easily add 32-bit numbers in one clock cycles and even 100-bit numbers. So on one hand, you can only go through at most 20 gates. On the other hand, you can add numbers that are 100 bits long. So you would think naively that performing such an addition would take at least 5 clock cycles, 100 by 20. At least 5 clock cycles, not one. So obviously, if there exist adders that can perform addition of 100-bit long numbers in a single clock cycle, and within one clock cycle you can traverse at most 20 gates, then clearly these adders that are used in modern microprocessors are not Ripplecarry adders. So this raises the question, is there another way to perform addition? Okay, clearly an RCA doesn't seem like such a great idea, in terms of delay at least. Okay, before we proceed, I want to define what the carry bits are in addition. And what we do is we look at the full adder. This is a combinational circuit. We know that if you give me the values of A and B and C0, then all the values of all the internal signals and the outputs are well defined. So let's define C0, C1, C2 up to Cn to be the carry bits that correspond to the addends A, B, and the carry bit C0. Okay? So these are the stable values of these signals in the Ripplecarry adder. Okay, and this is well defined because the simulation theorem tells us that in a combinational circuit, all the values of every signal are uniquely defined by the values of the inputs. Now, if I look at the correctness proof of RCA-N or RCA-I for any I between n minus 0 and n minus 1, then I know that that Ripplecarry adder is correct, and therefore if I look at the first I plus 1 bits of A, first I plus 1 bits of B, and C0, their sum is represented by the first I plus 1 bits of S plus Ci plus 1 multiplied by 2 to the power of I plus 1. Now from this equality I can conclude two things. I can say Ci plus 1 is 1 if and only if the left-hand side is greater than or equal to 2 to the power of I plus 1. And the second thing I can conclude is that the number represented by the first I plus 1 bits of S is simply the left-hand side divided by 2 to the power of I plus 1, where I take the remainder. So I take the remainder of the left-hand side when divided by 2 to the power of I plus 1. Okay. Now if I look at Si and Ci plus 1, and I ask myself, what is the cone of the Boolean functions that correspond to these two bits? Well, Si, its cone contains all the bits of A from position 0 to I, all the bits of B from position 0 to I, and C0. So in total I have here 2I plus 3 bits. Okay? And Ci plus 1 is also determined by the same bits, and one can show that each one of these bits is indeed in the cone of the corresponding output. Let me show you an example. Let's prove that C0 is in the cone of the Boolean function that corresponds to Cn. And the similar proofs would show that all the inputs belong to the cone of the Boolean functions that correspond to Cn, or the Boolean function that correspond to Sn minus 1. Okay? So indeed, let this denote A and this denote B. So here A is all 1s, B is all 0s, and C0 is 0. The output is written over here. Now I flip C0, I turn it into a 1. A and B remain the same, and this will be the sum. And now you can see that Cn here is 0, and Cn here is 1. So by flipping C0, I flipped Cn, and therefore C0 is in the cone of Cn. And you could do the same trick for every bit of A and every bit of B. And you could also use it to prove that every bit of A, every bit of B, and C0 are in the cone of, say, Sn minus 1. Okay? Good. So, what we conclude from the analysis of the size of the cone, that if A is a combinational circuit that implements an adder, and if the fan-in, this should be C. If C is a combinational circuit that implements an adder, and if the fan-in in C is at most 2, then the cost, oh no, this is C and this is C. Then the cost of C is at least 2n, and the delay of C is at least the log of 2n plus 1. Now, if we look at the RCA, we know that the cost of the RCA is theta of n, and that the delay of an RCA, with parameters n of course, is also theta of n. What this means is that here we're good, we're linear, the lower bound is linear, and we are linear. And here we're bad, because the lower bound is logarithmic, and the delay is linear. So the question is, could we do better? Our lower bound suggests that the delay should be logarithmic. Can we actually find an adder whose delay is logarithmic rather than linear? Okay, consider the following situation. We have two players. One player is called Bob, the other one is Alice. Bob thinks he's on the moon. Alice is on Earth. Bob is very bored. He's alone on the moon. He wants to entertain himself with Alice. Alice is willing to play along, and she suggests that they entertain themselves by adding numbers together. Okay, so here are the rules of the game. Alice holds the first k bits of A, the first k bits of B, and the carry-in bit C0. Bob holds the remaining bits of A and the remaining bits of B. Now, at the end, they should know the sum. So they don't need to know all the sum bits. It suffices that the union of the sum bits that Alice knows and the sum bits that Bob knows are all the sum bits. Okay? So together, they share all the sum bits. And it doesn't really matter if S7 is held by Alice or by Bob, as long as somebody holds S7. Now, because Bob is on the moon, communication is very costly and slow, so they want to compute it as fast as possible, and of course taking into account that communication is very slow. Okay, so let's assume that locally they can compute things very quickly, and if Alice wants to send a message to Bob, it takes quite a long time. Okay. So, Alice says, I have a great strategy. I'll just send you one bit. And you can guess which bit Alice is going to send, because recall that Alice holds the two strings A0 up to K minus 1 and B0 up to K minus 1. So Alice can locally compute S from 0 to K minus 1, and she's just going to send Bob a single bit. Which bit will she send him? She'll send him the bit CK. Good. So she promised to send him CK, and Bob is waiting for the bit. It takes a while, communication is very slow. And he asks himself, can I do anything while I'm waiting for Alice to send me CK? Now recall that Bob holds A from position n minus 1 to K, and B from position n minus 1 to K. And he actually wants to add these three numbers together with CK. This is his goal. He wants to compute this sum. Right? So can he do anything in the meantime without knowing the value of CK? Okay. Bob has an idea. The bit CK that he's about to receive is going to be either a 0 or a 1. Only two possibilities. And based on these two possibilities, he's going to perform the summation that he needs to perform. So Bob says, okay, I will compute answers for both cases, one for the case that CK is 0, and the other one for the case that CK is 1. As soon as CK arrives, Bob will select one of his pre-computed answers as the final result. So he will take A from position n-1 to k, B from position n-1 to k, compute the sum. You will also take A from position n-1 to k, B from position n-1 to k, and 1. This is under the assumption that the carry bit is 1. And then he will get another sum. Let's call it sum plus 1. And now he will just take a mux. This mux will be controlled by CK. This is the bit that Alice sends him. If the CK is 0, he chooses this input. If the CK is 1, he chooses this input. In any case, his output will be selected by the mux, and this will be the correct result. So, of course, it's a great game and very instructive. And in aftermath, Bob recalls that he has actually knew this before. And this is the design which is based on the game between Alice and Bob. So it's a recursive design. It's called a conditional sum adder. The base case when n equals 1 is simply a full adder. And now let's describe the reduction step. So this is the part that Alice holds. This is the part that belongs to Alice. Alice takes the first k bits of A and B and C0. She adds them. She has her local sum. And she sends CK to Bob. Now Bob computes two sums. One is the regular sum, A plus B plus 0, and the other one is A plus B plus 1. Okay, so he has these two different additions that he performs. And let's denote the first sum by S0 from position n-1 to k with a carry bit C0n. And the second addition under the assumption that the CK is going to be 1 is going to be S1 from position n-1 to k concatenate with C1n. Now CK controls a mux. In case CK is 1, you choose the right branch. If CK is 0, you choose the right branch. If CK is 1, you choose the left branch. And this will be your sum bits and your carry bit. And the claim is that the conditional sum adder is correct. Okay, so this is the part held by Alice. And this is the part held by Bob. Held by Bob. Okay, now we want to prove that the adder is correct. The proof is very simple. We will do it by induction on n. Let's just show the induction step, assuming that it's true, correct for n equals 1. And the induction hypothesis tells us that smaller CSAs are also correct, so it's actually complete induction. Good. So this is the part that refers to the branch done by Alice. Alice adds the first k bits of A, the first k bits of B, and C0. She uses a CSAK. And this CSAK outputs these bits of the sum and this bit of a carry, and we know that this equality holds because of the induction hypothesis. Now we have the part which Bob is in charge of. So Bob adds A from position n-1 to k and B from position n-k. And he has two types of addition. He has the addition with the carry in, which is 0, and the addition in which the carry in is 1. So if CK is 0, then he chooses this branch. So he actually is adding a 0 here. If CK is 1, he's choosing this branch. So either way, because of the correctness of these two CSA and the way the mux chooses one of these two outputs, we know that the last n-k of A, n-k bits of A, plus the last n-k bits of B, plus CK, the bit that he gets from Alice, equal the sum bits from position k to n-1 plus Cn with a weight of 2 to the power of n-k. Let me elaborate a little bit on the weights written here. You see, I did not multiply CK by 2 to the power of k, and the reason I didn't do it is that I think of the bits which are fed here and here as starting from position 0 and ending in position n minus k minus 1. Yeah? So I'm doing like a shift, an implied shift of the left part of A and the left part of B. Okay, so the actual weights of the bits here are not their indices, because they're indices subtracted by k. And this is why you don't see here 2 to the power of k. And this is why you see here the minus k in the exponent. Everything is scaled down by 2 to the power of k. So now to correct things, I have to multiply both sides by 2 to the power of k, and I add it with the equation of Alice. And I get 2 to the power of n times cn, this is from here, plus s from position n minus 1 to k, concatenated with positions k minus 1 to 0, so this is this part, plus this addend, ck times 2 to the power of k. And here I have the bits of A, and the left side of the bits of A over here, the bits of B added. I have C0 copied over here, and ck multiplied by 2 to the power of k. This appears in both sides, and after deleting it, I get the required equality, and that completes the proof of the CSAN. The delay analysis of the CSA with parameter n. Let's assume that n is a power of 2, and let's optimize the delay by setting k to be equal to n over 2. Namely, Alice and Bob both hold exactly half of the bits. The delay of a full adder is denoted by DFA, and the delay of CSAN satisfies the following recurrence. If n equals 1, it's simply the delay of a full adder. If n is greater than 1, then the delay consists of a delay of a CSA with parameter n over 2 plus the delay of a mux. Let's see why this is true. This is true because my paths either go through a CSA of size n over 2 and then through a mux, or they go through a CSA and then through a mux, or they go through a CSA and then through a mux. In either case, because k equals n over 2, all these three CSAs that work in parallel have a delay of CSA of n over 2, and this adds a delay of another mux because this is simply a row of muxes. So we have this recurrence, and we are familiar with this recurrence. Its solution is that the delay of a CSA is log n, L equals log n. Log n times the delay of a mux plus the delay of a full adder, namely big theta of log n. So this is a very nice delay, because this delay asymptotically equals the delay that the lower bound told us, that the delay had to be at least logarithmic. What about the cost? So we denote the cost of a full adder by CFA, the cost of a conditional sum adder with parameter n. Well, if n equals 1, it's just a full adder. If n is greater than 1, then we have 3 CSAs of size n over 2 plus our row of muxes. So we have here the recurrence f of n equals 3 times f of n divided by 2 plus theta of n. Now the solution of this recurrence, we saw this was recurrence number 3 in the chapter on asymptotics, is f of n equals big theta of n to the power of log base 2 of 3. Yeah, so this is roughly n to the power of 1.58. Okay, so this is much more expensive than a linear cost that we had in the Ripplecarry adder, but the delay is logarithmic, and it's very easy to use because you designed a CSA n simply by taking 3 half-size adders and a row of muxes. Let's continue with another adder. This adder is a very interesting adder. It's called a compound adder. It is a little bit different than a standard adder because it does not have a carry-in bit. It has only two add-ins, A and B, but it has two outputs, S and T. Notice that we don't explicitly write the carry-out bit. Instead, we have SN and TN. And the functionality is that the number represented by S has to be equal to A, the number represented by A plus the number represented by B, whereas T, on the other hand, has to output the sum of A and B plus 1. So we don't have a carry-in bit, and we do both computations that the carry-in bit is 0, the carry-in bit is 1. You could think of it as plus 0. And we don't call it a carry-out bit, we just give it another extra bit position. The reason we use this, S is simply the sum, and T is the incremented sum. It's the letter that comes after S to help us remember that we need to add the 1. Okay, let's try to view the problem of designing a compound ladder using the game of Bob and Alice. So here what we do is we take the input A and the input B and partition them into the left side and the right side. The same we do for B, and also for the sum we partition it into L and R. Notice that here I've written the SL a little bit longer, so this fellow is actually the carry out bit. And think of the situation in which I do not have a carry-in. The carry-in is 0. And I add AR and BR, I get SR, and I have a carry-out bit, which I denote by S prime K. Okay, so this is the game I need in order to compute the number represented by A plus the number represented by B without a carry-in bit, namely a carry-in bit, which equals 0. This is what Bob is doing when he's playing with Alice 0. So he's playing with two Alices. One is called Alice 0, the other one is called Alice 1. Both of them get AR and BR as input, but one of them does the standard addition and the other one does the addition with plus 1. Okay? So he's playing the same game with Alice 0 and Alice 1, and Alice 0 tries to compute AR plus BR. It locally keeps its sum. This will be the right part of SR, and it will send S prime K, this is this bit, to Bob, is the carry bit for the carry out bit for AR plus BR. Okay, so this is what Bob gets from Alice 0. Alice 1, on the other hand, computes the same sum plus 1. Locally, it gets the output, the right-hand side of T, and it sends to Bob T prime K, which is what would have happened if the carry-in bit here, if the carry-in bit here were 1, then I would have a carry out here, which is T prime K. So this is the bit that Alice 1 sends to Bob. Now Bob is, he's waiting for 2 bits, S prime K, T prime K. He computes AL plus BL plus 0, AL plus BL plus 1. And then when he gets S prime K, he chooses the right thing from AL and BL, and when he gets T prime K, he chooses the right thing from the sum of AL plus BL, and that will be TL. Let's see the design. So the design for a compound adder, the implementation for n equals 1, well, you use a full adder to compute the sum plus 1, and you use a half adder to simply compute the sum. And the reduction step is as follows. This is the part which is computed by both Alices. So this is, So this is Alice 0 and Alice 1. So you see, let me draw it a little bit differently. Will be more instructive. This is the part that Alice 0 does, and this is the part that Alice 1 plays. So you see ls0 locally computes the sum from position 0 to k minus 1, and the carry out bit is prime k, and ls1 locally computes the bits of the sum t from position k minus 1 to 0, and the carry out bit t prime k. And how do ls0 and ls1 work? Well, they simply employ a compound adder with k bits of input. Okay, so doing this part and this part is done by this compound adder. Okay, S prime k is of course sent to Bob. T prime k is also sent to Bob. So I didn't draw these wires, but they exist. Let me draw them and erase them. So the first wire simply goes from here to here, and the second wire goes from here to here. But I don't want it to look like a spaghetti, so let me get it out of the picture, not to clutter things. So this bit is again this bit, and this bit is again that bit. Very good. Now, what does Bob do? We're now on Bob's part. Bob takes the left-hand side of A and B, he feeds them to a compound adder of size n minus k, and this compound adder outputs S double prime and T double prime, right? Now, one of them is the sum, the other one is the incremented sum. He uses a mux, which is controlled by S prime k, to output the left-hand part of S. He uses another row of muxes, controlled by T prime k, to obtain T from the left part of T. Both of these muxes share the same inputs. So S prime is fed both to here and to here, to the 0 terminal of these muxes, and T prime is fed both to here and to here, to the 1 terminal of the muxes. And this completes the description of the circuit. Let's see an example. Let's say that A is 0, 1, 1, 0 and B is 1, 0, 0, 1. Well, in this case, the lower part, the right-hand part of A will be 1, 0, and the left-hand part of A is 0, 1. With B, the right part is 0, 1, and the left part is 1, 0. The sum is 1, 1, and this bit is a 0, and the incremented sum is going to be, you add 1 plus 2 plus 1, that's 4, so the incremented sum is 1, 0, 0. So this bit is a 1, this bit is a 0, these two bits are 1, 1, and these two bits are 0, 0. Okay, so now this bit is a 0, this bit is a 1. Let's perform the addition that Bob does. It's basically the same addition, right? So here it will be 0, 1, 1, and here it will be 1, 0, 0. Now, here I select the 0 input, so this will be 0, 1, 1. And here I select the 1 input, so this will be 1, 0, 0. So, if I input A, which is 0, 1, 1, 0, B, which is 1, 0, 0, 1, then, things are going crazy. Here we go. Then our sum is simply 1, 1, 1, 1. You see 2 bits of 1 here, 2 bits of 1 here, and the extra bit is a 0 over here. And our T, what is going to be our T? Our T is going to be 0, 0, 0, 0, 1. So this will be 0, 0, 0, 0, 1. And you see that the design performed the compound addition correctly. Okay. We claim that the compound adder is correct. Let's see the proof. There are 2 ways of proving the correctness of the compounder. One way is to prove it directly. You can see a proof in the book. What I will show here is a reduction to a conditional sum adder, and I will consider 2 separate outputs, the S output and the T output. In the case of an S output, I will argue that the compound adder has the same output as a CSA with the same inputs, and carry in equals 0. And for T, I will argue that the compound adder outputs the same output as a CSA with the same A and B, but C0 equals 1. And let's see one of these two arguments. Let's assume that I want to prove the correctness of the T output. So what happens here is I took A and B, and the right part of A and B, I added a 1. I got the right part of T. I sent the carry out bit, just as I do in a conditional sum adder, and I send it to this mux, and this compound adder computes the sum and the incremented sum and does the selection correct, as you would do it in a conditional sum adder to get the right result. Okay, so just a simulation argument which says that this circuit does the same thing as a conditional sum adder for the S output, and the same thing as a conditional sum adder for the T output, where in the T output the C0 is 1, and in the S output the C0 of the CSA is 0. Let's analyze the delay of the compound adder. I claim that again, I'll use powers of 2 and assume that k is n over 2. Then the delay satisfies the following recurrence. Let's try to understand why this is the recurrence. I have here paths that go either through a compound adder or through like this, or like this, or like that, or like this. And you can see that the longest paths have to traverse a compound adder of size n over 2 plus a single mux. So this explains this part. And we already know the solution to this recurrence. It gives us log n. This L is log n. Delays of a mux plus a full adder. This is big theta of log n. So it's a nice adder. What about the cost? Well, if we look at the circuit, then we have two compound adders of size n over 2, and these muxes, this is n over 2 and this is n over 2, so we have here in total n plus 2 muxes. So the recurrence is, there's a missing 2 here. So we have two compound adders of size n over 2 and two rows of muxes of size n over 2 plus 1. So this is big theta of n. And so we have here the recurrence f of n is 2 f of n divided by 2 plus big theta of n. And we know that this means that f of n is big theta of n log n. And therefore the cost of the compound adder is n log n. Surprise! The compound adder is much cheaper than the conditional sum adder. The conditional sum adder had a cost which behaved like n to the power of log base 2 of 3, which we said was more or less like 1.58. And here we have n times log n. This is much smaller than that. And surprisingly, we were able to reduce the costs using this design, because in the recurrence we only have 2 instances of size n over 2 instead of 3. Before we finish, I would like to emphasize that if I look at the Ripplecarry adder, then I see that I have the following relation between the sum bit, the 2 bits of the addend, and the carry bit. The sum bit is simply the XOR of these 3 bits. Now I can XOR to both sides of this equation. I can XOR SI XOR CI, and therefore I will have here XOR SI XOR CI, and here I will have XOR CI XOR SI. Now notice that SI XOR SI is 0 and CI XOR ZI is also 0, so I get that CI equals AI XOR BI XOR SI. So I can compute the XOR bits from the sum bits and the 2 addends, or alternatively I can compute the sum bits from the 2 addends and the carry bit. Good. Let's summarize. We defined binary addition. We presented 3 adder designs: the Ripplecarry adder, the conditional sum adder, the compound adders. We showed that the problems of computing the sum bits and the carry bits are equivalent with respect to constant time linear cost reductions. What this means is if I have Ci, Ai, and Bi, can compute Si in constant time. These are 2 XORs. And if I have all of these bits, I can compute all of the bits of the sum with a linear number of XOR gates. Okay, now the cost of every adder is big omega of n, and the delay is big omega of log n. We saw this because of the lower bounds, and therefore the problems of computing the sum bits and the carry bits are equivalently hard in terms of the asymptotic cost. Okay, I focused in this talk on how to compute the sum bits. You could focus on how to compute the carry bits. Once you know the carry bits, you know how to compute the sum bits. The main design methodology that we use today is divide and conquer. We are somewhat surprised by the fact that the compound adder turns out to be cheaper asymptotically than the conditional sum adders. And of course, we're left to show an adder that has both linear cost and logarithmic delay, but this is beyond the scope of this course. Thank you very much.